is actually sort of the physics of what's going on when you put an impulse through this response. When convolving a filter with an impulse image, we get back the filter as a result, right? So in other words, by doing the convolution, we flipped it and then we rotate it, it flips again. So if I take an impulse and I convolve it with H, I get back H. All right, well then how about the following? If we convolve an image with an impulse, what would we get? Well, A, a blurred version of the image. B, the original image. C, a shifted version of the original image. And D, you have no idea. So you don't get any credit for D. Even if D is true, you have no idea, you get no credit for D. All right? The answer, actually, is the original image. The way to think about that is, when I was doing the convolution or the correlation, there's really no distinction between what's the image and what's the filter, right? It's just an operation where I combine these things. So before, when I was convolving an impulse with a filter and getting back the filter, we were thinking of the impulse as the image and the filter as the filter. But you could have just thought of as the filter as the image, and the impulse is the thing you're doing the convolution with. And basically, all the impulse is doing is pulling out the single pixel and sticking it in the result. So when you convolve something with an impulse, you get back just the original image. All right. One more thing. In order for all of this to work, we need a property called shift invariance. And shift invariance is basically that your operator behaves everywhere the same way. So if I have a couple of pixels over here on the left and I apply my operator, if I had the same pixels over here on the right, oh, this is my left, my right, your right, turn around. Okay, or look, never mind. If I have them up and down, right, if I have a couple of pixels up here and I apply a filter, I get the same values if I have a couple of pixels down here and I apply the filter. That means that I can shift things around and do the addition and get my entire image back. As we said, because convolution or correlation are built on multiplication and addition, these are linear operators, making the whole notion of filtering a linear operation. And this means that convolution has some very useful properties. For example, it's commutative. All right, so F convolved with G is the same as G convolved with F. Remember that whole idea about which is the impulse and which is the filter? It's also associative, so that here we wrote out the associative property of convolution. We're going to take advantage of that in just a minute. It has a unit impulse, it's the identity, so that's when we talked about that if you convolve any function with the identity, you get back that function. And then here's a cool one. Differentiation, of course, is just the limit of subtraction and then a division. And division is the same as multiplication, it's 1 over in that case. So differentiation is a linear operator. Now, you may have remembered that from calculus, right? So the derivative of a times f, where a is a constant, was just a times the derivative of f. And the derivative of f plus g was the derivative of f plus the derivative of g. So differentiation is also a linear operator, and because of associativity, we get this cool property here, that the derivative of a convolution is the same as taking the derivative of one of the elements and then convolving it with the second. And we're going to make use of that when we do edge detection and gradient finding in a little bit. I want to talk just a quick second about computational complexity. I mentioned it before. As we said, if your image is n by n and your kernel is m by m, or we'll call it w by w for sort of width, and it's easier to say w being different than n because I do that exactly. Okay? So the question is, how many multiplies do we need? And we said before that we need n times w or n squared w squared. Doesn't n squared w squared sound better than n squared m squared? Because when I say n squared m squared, you have no idea what I'm saying if I say it quickly. N squared w squared works. And that can get sort of big. So there's a cute little property. Sometimes your main kernel, your filter, can be created by convolving a single row with a single column. And when that's true, you can take advantage of the associative property in terms of how we do this. And this is what's referred to as a linearly separable kernel. So let me show you an example. So here we have a single column, and here we have a single row. And just think of zeros being around it. If I convolve this column by this row, I would get out this new H, which has 1, 2, 1, 2, 4, 2, 1, 2, 1 in it. Okay? So C convolved with R equals H. See, this is why we don't use my handwriting. Let's suppose we wanted to filter something with h. All right? So that would look like this. We have a function g that we're going to create by convolving f with h. But we said that c convolved r is the same as h, so that convolves f. And because of the associative property, c convolved with r, then convolved with f, in order to get our new function, is the same as c convolved with r convolved with f. And the reason that's better is that I can do 2 column convolutions instead of 1 squared. So now, instead of being w squared n squared, it's 2 times w times n squared. And that used to be very important when computers were not quite as fast, but it's still reasonably important because, for example, if w is, say, a 31 by 31, that's a factor of 15 difference, all right? So that's more than an order of magnitude. Anytime you can do anything that buys you an order of magnitude for not a lot of money, you should go ahead and make that purchase because orders of magnitude are hard to come by. So here's a nice way of doing that. So when we do various kinds of smoothing, etc., often we use linearly separable filters, and you can just apply them. Here's another quick quiz. True or false? Division is a linear operator. Okay? A, false, because x divided by y plus z does not equal x over y plus x over z. True, because x plus y divided by c is the same as x divided by z plus y divided by z. And c, I have no idea. Okay? Again, c might be true, but it's false. No, c is true, but you get no credit. The answer is true in this case because it's division by a constant. All right? So in this case, if I'm dividing by z, so if I sum up x plus y divided by the z, it's the same thing as x divided by z plus y divided by z. Much later, we're going to be doing perspective projection, and you're going to end up having to normalize the x and y values by the z value of a point, and then the z is actually going to be a component of the element. And since that component can change, that's not going to be a linear operation. But in general, division is a fine linear operation because the last time I checked, dividing by 2 was the same as multiplying by 0.5. And multiplication is part of the linear operation. One thing that comes up when doing filtering is what to do about the boundaries. Because you might ask, what happens when your filter falls off the edge?
What happens when your filter falls off the edge?
Megan has been rehearsing this all week. Outstanding. Well, basically, it's undefined until you define it, all right? So you have to think about what size operation you want. So that can be illustrated like this, okay? And here we're going to use a little bit of old MATLAB nomenclature. They've changed it because the old MATLAB nomenclature actually makes it clearer. So here I've got a function f, and I'm filtering it with g. And you might try to think about, well, what's the size output that I want? And there's sort of 3 different possible sizes. One is when g just touches that corner, I start to get a response. So if I think of the center point of g as the reference, I would actually get a box that's bigger than the original function. Okay? The flip side is, if I want to make sure that all of g is actually touching f, then I'm going to, again, using the center point, I end up with a smaller output than the original. And that's used to be referred to as valid, since all those points were in fact correct. But the problem is, when I filter a 55 by 55 image, I really want to get back a 55 by 55. I don't want to get back a 58 by 58 or a 52 by 52. What I want is referred to as the same. So here you see that we put that filter with its middle at the corners, and we get back the same size. So the problem, of course, is what's underneath these pixels here that are sticking out? And basically, when you do filtering, you have to tell the system what you want there. MATLAB has a couple of ways of thinking about how to do this, right? And we're going to use, again, old MATLAB nomenclature, and then I'll tell you about the new one. So there are a couple of different methods. The first method is called clip. Clip basically means I assume that that outside boundary is black. I then apply my filter, so here I can see my filter, and when I pull out the image, you can notice that this thing has gotten kind of dark at the edges. And that makes sense because that black has leaked in, all right? But that's referred to as clipping. Another method is called wraparound, and it's kind of a weird method. It has to do with some Fourier analysis that we'll talk about later. Basically, it says that I assume my picture continues and wraps around, which means that you'll see this stuff filled in here. That's the stuff that comes from this side of the picture. It's easier to see up here, right? These red peppers came from down here, and the yellow straw comes from over there, all right? And that was under assumption that what you were actually looking at was a periodic signal. So if you were looking at a periodic signal, the next thing that would happen would be the stuff that was at the start of it. Well, in filtering, that image filtering, that doesn't work so well. Here I'm going to apply the filter, and then I'm going to cut back to the original size image, and you'll notice that there's some red stuff here. Where did that red stuff come from? Well, it actually came from the bottom because it got wrapped around. There is a method that's called copy edge or replicate, where you just basically extend out, right? So I just extend out the same value. And then I run my filter, and I pull out my picture, and that's reasonable, okay? The replicate method is an easy one, and it gives you a reasonable result. It basically says that the image sort of stays the same. Now, the problem is that the statistics, of course, are different, right? Because you have this nice varying image, and then you make everything be sort of the same going out. So another method is called reflection, okay, or sometimes called symmetric. And what that does is you reflect the image out, and here, I just did that. In fact, here, let me draw right here. Here's the reflected edge. It's actually, if I erase it, hard to see that edge, right? Because I basically, I take the image and I fold it back out again, all right? So then I take that, I apply my filter, and then I pull out the image, and it actually does a pretty good job. So often you either want to do what's called replicate or copy the edge or reflect across the image. In new MATLAB, these are expressed using this function called IMFilter, which comes from the image processing toolbox, and you can do, you put in a value, it just puts that value in. So if you put in 0, it's like clipping. You can wrap around with circular. And then the copy edge is replicate, and reflection is symmetric. And typically, you'll use either replicate or symmetric.
So which is your favorite option to deal with edge issues? Load up the image package, read an image, create a Gaussian filter. Remember, Gaussians are special. Now when you apply it, specify an edge parameter. Passing in 0 is equivalent to the default. You can see the black seeping in along all the edges. This is because we passed in 0. What happens if we put in some other number? Try it out. What about circular? If you look closely, you'll see the green seeping in on this side and a little bit of red on the opposite side. Replicate. Replicate is not too bad, no obvious effects. And lastly, symmetric or reflect across edge. Not bad either. Actually, not too different from replicate. Feel free to experiment with these different options, filter sizes, and sigmas.
The reflection method of handling boundary conditions in filtering is good because A, the created imagery has the same statistics as the original image. B, the computation is the least expensive of the methods. C, setting pixels to 0 is quick. Or D, none of the above. Well, C is true but irrelevant. B is false but irrelevant. A is the correct thing. The imagery that you create by doing that reflection has the same statistics, and I guess I should have also written no obvious edge induced, right? When I did that reflection, it was actually hard to see where those edges were. For the very last part of this lesson, we'll do some simple analysis about what different filters will do, and then we'll do more sophisticated filtering later. Here we have a picture. There's the original one on the left, somebody's eye. Maybe you know whose eye it is. And I convolve it with that filter. That's an impulse. What do you get back? Well, what do you get when you convolve an image with an impulse? You get the original, and there it is. It's no change. Okay, so when you filter with an impulse, all right? So here's a slightly interesting one. What happens if I've got an impulse, but it's not centered at the reference point, but it's shifted over right by 1? Well, what's going to happen is when I place my filter down in the middle, it's going to go get the pixel from the right and put that down at the reference point. And then I move it over and get to right. Now, whether I get the one on the right or the left will depend upon whether I'm doing correlation or convolution. Remember, correlation, I just move it around. Convolution, I flip it over and then move it around. But what you're going to end up with is a shifted image. So in this case, you'll shift it to the left if you're doing correlation. So by shifting the impulse, you get a shifted function. And that's because the idea is that the center coordinate here is 0, 0. All right, what about this?